A very good morning to all. Myself Jesuharan Samuel. I am from Electronics and Instrumentation Engineering Department of PSN College of Engineering and Technology. The lecture which we are going to discuss today is about measurement of voltage and current. So, the main parameters in electrical measurements are voltage and current. So, the measurement of voltage and current is to be done by using any one of the measuring instrument. First of all, we should know what is a measuring instrument. So, what is an instrument? An instrument is a device. A measuring instrument is a device which is used for comparing unknown quantity with the unit of measurement or standard quantity. In other terms, we can say it as it is a machine or a system which is designed to maintain functional relationship between prescribed properties of physical variables and which could include means of communication to human observer. The instruments can be broadly classified into two: absolute and secondary type of instruments. Under the secondary type of instruments, it can again be subclassified as indicating, integrating and recording type of instruments. Let's see it in detail. Classification of instruments. Absolute instruments. It is the one which gives a quantity to be measured in terms of instrument constant and its deflection. Every instrument has an instrument constant and every instrument has a deflection parameter which is the measured quantity. So, the quantity is measured in terms of only instrument constant and its deflection. While the secondary instruments, the deflection is given in terms of magnitude of electrical quantity to be measured directly. Here the measurement is done directly and there is no need of instrument constant. So, the output will be displayed directly in the secondary instruments. So, what is the necessity of secondary instruments? It needs a standard. So, every secondary instruments needs a standard with which it needs to be compared and calibrated. So, these instruments are required to be calibrated by comparing with another standard instrument before being put into use. We use secondary instruments mainly in all the electrical measuring industries everywhere. We have already seen the main classifications, and again the secondary instruments are classified as indicating, recording and integrating instruments. Let's see what are they. And indicating instruments. The indicating instruments indicates the magnitude of electrical quantity at the time when it is being measured. These are given by a pointer moving over a graduated dial. While the recording instrument, it keeps a continuous record of the variation of the magnitude of electrical quantity over a defined period of time. So, the instrument readings can be recorded and it can be seen later. So, for example, at a particular 10 seconds, reading can be done, and after some period of time, it can be done. After some 1 minute, then again a recording can be done. So, these all can be displayed simultaneously and can be viewed for observation. The integrating type instruments. One of the main example is an energy meter, the household energy meter. So, integrating type instruments, as we all know, integrating means for a period of time. That means the measurement is done over a period of time, not at a particular point of time, it is done over a period of time. So it is defined as instruments which measure the total amount of quantity of electricity or energy supplied over a period of time. For example, the energy meter, which gives the recording of energy consumed over a particular month or particular period of time. So we have all seen, we have so far seen the main classifications of instruments. So what are all the necessities of indicating instruments? So what are all the essentials? So indicating instruments indicates the value of quantity being measured at the time which is being at the time of measurement. So it consists of a pointer which moves over a scale which is attached to a moving system. The moving system is pivoted with the help of a bearing system. The moving system is subjected to three following torques. A torque means a twisting or turning moment of force, that is called torque. So since it is a movable instrument, it is a rotating instrument, it contains three torques. One is deflecting torque, second one is controlling torque, third one is damping torque. The deflecting torque or operating torque, the controlling torque or restoring torque, and a damping torque. First one is deflecting torque. So the deflecting torque is produced by making one of the magnetic, heating, chemical, electrostatic and electromagnetic induction effect of current or voltage, which causes the moving system of the instrument to move from its zero position. The deflecting torque, the magnitude of the deflecting torque depends on the value of the electrical quantity which is to be measured. So it can be produced by many methods, by the magnetic, heating, chemical, electrostatic or electromagnetic induction effect. So there are many methods of producing this deflection torque. So it depends on the type of instrument which we are using. The second one is controlling torque. So the controlling torque, so we have already produced a deflecting torque. So the torque must be controlled at a particular point of measurement. The pointer should not move beyond that. So we need a controlling torque to make steady the pointer. So the controlling torque is defined as the magnitude of the moving system. The control would be somewhat indefinite under the influence of deflecting torque. I have already said it may be indefinite unless any controlling torque is existing to oppose the deflecting torque. So it increases with the increase in deflection of the moving system. As the deflection increases, the controlling torque which is needed is also increased. So only under the influence of controlling torque, the pointer will return to its zero position. So whenever the source or the input electrical voltage or current is removed, the pointer should return back to its initial zero position, which is possible only by using the pointer. So without the controlling torque, the pointer will swing at its maximum position and will not return to zero after removing the source. So there are two types of control. One is spring control and gravity control. So spring control. So control is a point when deflection and controlling forces are equal. That is, the pointer is at rest only when the deflection and controlling forces are equal. So this torque, for this, a control is to be produced by either a spring control method or gravity control method. A controlling force is produced by either a spring control method or gravity control method, which is proportional to the deflection force. First one is spring control. In the bottom right corner, you can see the diagram of a spring control system. Here we can see a spindle. A spindle is a, you can see this is a spindle. A spindle is a rotating part, which is connected to which is pivoted on bearings. The spindle is surrounded by two control springs. One is A and another one is B. These control springs are wound opposite to each other. And in this spindle, this pointer is attached, which moves over the scale. The spindle rotation of the spindle is depending on the deflection force. So when the pointer is deflected, one of the spring A or B unwinds itself. Unwinding means it gets loosened, unwinds itself, while the other one is twisted. It is being twisted. That is the force is increased. It is get tightened. So the twist in the spring produces the controlling torque. The twist in the spring produces the controlling torque, which is proportional to the angle of deflection of the moving system. So the controlling spring gets twisted, thereby producing a controlling torque to the spindle. So the amount of controlling torque produced is proportional to the angle of deflection. So as the angle of deflection is more control torque is produced. As the angle of deflection is less control torque will be produced. The scale of spring control type instrument is the deflection torque TD is proportional to the input current I. Also, controlling torque is proportional to theta. So the deflection torque is produced by the input source current. So it is proportional to the I. TD is proportional to I. While the controlling torque is proportional to the angle of deflection. So how much angle the spindle is deflected, that much controlling torque needs to be produced. So controlling torque TC is proportional to theta. So the pointer comes to a steady state position when both these torques are equal. That is, controlling torque TC is equal to deflecting torque TD. Therefore, when these torques are equal, theta is proportional to I. That is, the angle of deflection is proportional to the input current. Another one control is gravity control. In gravity control, the gravitational force by using a weight is used to control the movement of the pointer. Here a small adjustable weight is attached to the spindle of the moving system, such that the deflecting torque produced by the instrument has to act against the action of gravity. So here you can see the diagrammatic representation of a gravity control. Here you can see the spindle is connected with the spindle over which the pointer is rotated is connected with a control weight, which is hanging downwards. So this control weight is W. Here we can see, here the control weight is W1, while the zero or balancing weight is W2. So here the pointer is now at zero position. So this is the pivoted spindle. One can see the pivoted spindle in the center. Theta is the angle between the weight, control weight W, and the angle of a line drawn from the center of the pivoted spindle. We can clearly see it in this graphic, this vector diagram. Here we can see the angle of deflection theta is the angle between the control weight W1 and its two components, sine component, and there are two components, sine component and cos component. So theta is the angle between the weight W1 and its cos component. So we can extend this line beyond this W1 cos theta, and we can again draw a we can draw a circle, so that an angle of theta is again replicated here. So this is the angle of this angle theta is the angle between this pointer and this weight W. In the gravity control, a small adjustable weight is attached to the moving system. We have already seen, in such a way that the deflection condition produces a restoring or controlling torque. So we all know the weight produces the controlling torque, produces the gravitational torque, while W2 is for balancing the weight of the pointer, for maintaining the weight of the pointer. So the control torque, the equation for control torque is W1 sin theta into L. So W1 sin theta into L, or W1 L sin theta. So the angle of deflection sin theta is proportional to the controlling torque, while the input current I is proportional to the deflecting torque Td. At the steady state position, deflecting torque is equal to the controlling torque, so I is proportional to sin theta. So we have seen two torques so far. One is deflecting torque, another one is controlling torque. A deflecting torque is for producing the movement of the pointer, while the controlling torque is for controlling the movement of the pointer to maintain a steady state position. The third one is a damping torque. We have already seen that the moving system will tend to move under the action of the deflecting torque. So on account of control torque, it will try to occupy a position of rest when these two torques are equal and opposite. But even after producing controlling torque, due to inertia of moving system, the pointer will not come to rest immediately. So due to inertia, the pointer won't come to rest immediately, but oscillate about its final deflected position. So from this position, to maintain a steady state, we need a damping torque. The damping torque is to be developed by using a damping device attached to the moving system. So there are three types of damping torque, which is proportional to the speed of rotation. There are three types of damping torque. Depending upon the degree of damping introduced in the moving system, the instrument may have any one of the following condition: either critically damped, under damped, over damped, or critically damped. So of the three conditions, the first under damped condition is Yeah, the response is when the response is oscillatory. When the response is oscillatory, the condition is called as underdamped condition. Only when the response is sluggish, that is when it rises slowly from its zero position to final position. You can see here, when the overdamped condition, the response is sluggish and it rises slowly from its zero position to final position. So this is called overdamped condition. In the critically damped condition, the response settles quickly without any oscillation. Here we can see the critically damped condition, the graph is in the middle. The response settles without giving any sluggish response. So the underdamped condition, the response is oscillatory. In the overdamped condition, the response is sluggish, while in the critically damped condition, the response is a quick response, quick settling response. So there are four types of damping which can be produced. One is by using air friction or pneumatic damping. So air friction or pneumatic damping, both the friction uses air. So in the first one, we can see the left hand side diagram. We can see the pointer which moves over the scale is connected to the spindle, while the spindle is connected to the air chamber. Inside the air chamber there is a piston. So as the pointer moves here and there is a movement of the piston upwards and downwards. So the chamber is produced, already the air chamber is filled with air. So when the pointer is at a steady state position, that is after producing a controlling torque, when the pointer is at a steady state position, due to the air friction in the chamber, it will not let the pointer and the spindle to move further. Due to the air friction, the pointer and the spindle and the pointer connected to it will not move further, as the piston will hold its position in the air chamber. While in the another one, this is a sector shaped air chamber. Here it is a sector shaped air chamber. Here we can see the spindle is connected to the vane, rectangular vane, which moves inside the sector shaped air chamber. So it moves inside the sector shaped air chamber. It is a thin aluminium vane which moves with some small clearance in a sector shaped chamber box. So any tendency of the moving system to oscillate is damped by the action of the air. So due to the pneumatic action of the air, any further movement is stopped or damped. While in the first one, a light aluminium piston, the piston which is used here is a light aluminium piston, is attached to the spindle of the instrument and is arranged to move in a fixed air chamber closed at one end. So the cross section of the chamber may be either circular or rectangular. So the clearance area between the piston and the side of the chamber is uniform. So the clearance area is uniform in both the sides. So the compression and suction action of the piston on the air in the chamber damp the possible oscillation. As I have already told, the compression and the suction action will damp the oscillation of the system further. The next third type of damping method is eddy current damping. So eddy current damping is the most efficient of all the three methods of damping. So eddy current damping, all the first two methods use air principle, air or pneumatic principle, while the eddy current damping uses electrical parameter itself. So it is mostly used. It's the most efficient type of damping. Here a thin disc. Here we can see a thin aluminum disc. It is usually of copper or aluminum. Is mounted on the spindle. Here we can see the spindle. Over the spindle, in the spindle, a thin aluminum disc is mounted. The aluminum disc moves in a magnetic field. Here it's a magnetic field is placed. It is called as the damping magnet. The north and south pole of the damping magnet is indicated. So the aluminum disc moves in the magnetic field of the permanent magnet. So when the aluminum disc moves here, the lines of force are cut. The lines of force are cut. Here we can see the metal former, the aluminum metal former. In the right side, we can see the aluminum metal former, a circular aluminum metal former. Here, the north pole and south pole of the magnet is indicated. So, as the circular disc moves inside the magnetic field, the lines of force of the magnetic lines of force is cut. So when the lines of force are cut, here the magnetic lines of force are indicated here. So when it is cut, eddy current is being set up. So eddy current is being set up. So we are, as we all know, the force that exists between the current and the magnetic field is always in the direction opposing the motion, and therefore provide necessary damping. We all know the eddy current is produced. The eddy current direction will be in the opposite direction to the source which is produced. The eddy current direction is in a direction such as to, it moves in a direction such as to oppose the motion of the such as to oppose the source which produces it. So the movement is damped. So the magnitude of induced current and therefore of the damping force which is dependent on it is directly proportional to the velocity of the moving system. So when lines of force are cut, eddy current is set up. So that force which exists between the current and magnetic field, that eddy current force is always in the direction opposing the motion and provides the necessary damping. So the magnitude of the induced current and therefore of the damping force which is dependent on it is directly proportional to the velocity of the moving system. Another one damping method is fluid friction damping. Here the rotating spindle moves inside the rotating spindle is connected with a disc. Here we can see it is connected with a rotating vane. Which is placed in the oil. So there is a friction. Fluid friction is produced by using a friction oil. So as the spindle is rotated, the disc has to oppose the fluid friction. There in the initial method, the era of pneumatic damping, the disc has to move against the air force, air damping, has to move against the air. Here the disc has to move against the first one, it has to move against the air friction. Here it has to move against the friction produced by the fluid which is placed inside which is placed around the disc. So this fluid friction opposes or damps the motion of the pointer or the spindle. So a fluid friction damping can be obtained easily with the help of this setup of setting up of arrangement. So for the measurement of voltage and current, there are many type of voltmeters, and for the measurement of voltage, and many type of ammeters for the measurement of current. So they all can be subclassified as moving coil type, permanent magnet type, electromagnetic type, or dynamometer type. Then moving iron type, which is classified as attraction type or repulsion type. Third one is induction type, which is classified as split phase or shaded pole type. Fourth one is thermal type, which is hardware, which contains hardware type instruments, AC and DC instruments, and rectifier type of instruments. So all these instruments work on the principle of these three torques. All of these instruments work on the principle of these three torques. What are they? They are deflection torque, controlling torque, and damping torque. Deflection torque, controlling torque, and damping torque. So there are many type of instruments. So we have all seen, we have already seen the type of instruments: indicating, recording, and integrating type of instruments. So the ammeters and voltmeters, they mostly come under the indicating type of instruments. So indicating type of instruments, we can see the pictorial representation that the pointer moves over a scale, while the energy meters or watt meters, they all come under the integrating type of, the energy meters come under the integrating type of instruments, since it measures the quantity of electricity or electric energy supplied over a definite period of time. So far we have learned what is a measuring instrument. So far we have learned what is a measuring instrument. It is a device which is used to measure a input quantity by comparing with another one standard quantity. So the classification is absolute and secondary instruments. So of the secondary instruments, we have seen indicating, recording, integrating type instruments. So of the indicating instruments, we have seen the three main essential torques: deflecting torque, controlling torque, and damping torque. So what is the deflecting torque? We have discussed. It is the torque which is produced by any electrical quantity which is to be measured. It can be produced by any means, by either heating or a chemical or electrostatic effect or electromagnetic effect. While the controlling torque is produced by the controlling spring action, which is called spring control or gravitational control. So it is used to make the pointer to rest at a steady state position. So without the controlling torque, the pointer will not return to its zero position on removal of the source, producing the deflecting torque. So otherwise the pointer will swing at its maximum position and will not return to zero. So to make that, we are using a controlling torque. We have seen the spring control. The spring control is produced by using the twisting moment of the spring. The twisting moment of the spring which produces the controlling action, which is proportional to the deflection of the moving system. So theta is proportional to input current I. In the gravitational control, we have seen there is a control weight which is attached to the spindle. So that's another one balance weight. So this control weight provides the gravitational control which is necessary for controlling the movement of the pointer to go further. So here the current is proportional, that is the at steady state position the deflecting torque is equal to controlling torque. So at that time the current is proportional to the angle of deflection sin theta. Then finally we have seen the damping torque. Here the damping torque is produced by any one method, air friction or pneumatic damping. The air friction is produced by connecting the pointer to the air chamber. In the eddy current damping, here the aluminum disc, here a spindle is connected to the aluminum disc which moves over the damping magnet. So eddy current damping is the one of the most important damping method. So it moves moves around the magnetic field. So the magnetic lines of force are cut by the aluminum disc. So when this disc moves inside the magnetic field of permanent magnet, lines of force are cut and eddy current are set up. So the force that exists between this current and the magnetic field is in the direction opposing the motion and which provides the necessary damping. So the magnitude of the induced current and also of the damping force is dependent on it. It is dependent on the velocity of the moving system. Finally, we have seen the fluid friction damping. Here the friction is produced by the placing the spindle inside a fluid chamber where the aluminum vein moves against the fluid friction. So the friction causes the spindle to come to rest immediately. So these are all the basic technique used for the measurement of voltage or current by using any one of the measuring instruments. So these are all the basic parameters which is to be known earlier. So after that, in every instruments, in induction type instrument, in permanent magnet movement type instruments, in dynamometer type instruments, in rectifier type instruments, they all work based on this common principle. Only thing, the deflection force is produced by the different actions. So these are all the basics of measuring instruments which are used to measure voltage and current. Thank you.